Okay, perfect. So, yeah, we can start.
Yep.
Perfect. Okay, so hi everyone again. Now in this hour we are gonna follow up from what Taco has been explaining to you in the first hour about how to actually leverage the geometric structure of many of the problems that we encounter in practice in order to break this course of dimensionality, to break this like a bad pessimism news that we had on Monday. Okay, so boom. Okay, so today, so in this lecture, we are gonna hopefully try to connect the tool that Taco has introduced to you 1 hour ago of invariance and equivariance with the notions, of course, of dimensionality that I described last time. We are gonna also complement this notion of invariance with another prior that we are gonna define as scale separation. And we are gonna see how we can combine these two priors together into a pretty like axiomatic and first principle construction that we call this geometric deep learning blueprint. Okay, so let's start right away from the first part. So remember the goal in machine learning, at least in the supervised setting, is to learn an unknown function, f star, that and this I'm also using it to recall some notation. And so what Taco has been presenting you is that one can actually open the function space somehow. And instead of looking at X as the space of very high dimensional functions, now we can see the input space as a space of signals that are defined over a certain domain omega. And so this domain omega can be, sorry, let me just minimize the, okay, perfect. Okay, so this domain omega can comes with interesting transformations that are really deeply associated with the nature of the signals that live in this domain. For example, if the domain is a set, there's a natural transformation on a set, which is less to permute the its elements. If the domain is maybe some element of an Euclidean space, we can rotate or we can apply a rigid transformations of this domain, or we can even like, if I have a grid of pixels in the continuous case, we can think about like stretching the domain. And what is interesting, and Taco explained to you, is that these transformations, they can be combined together. And the notion, the mathematical notion for this combination is what's called a group, right? So we can take two transformations and compose them together to get a new transformation. And the other thing that also Taco explained is that these transformations of the domain can be upgraded or lifted to linear transformations of the signals that live in this domain. Right. So in other words, more precisely, if I have some transformation that maps a point in the domain omega to another point in the domain omega here, we can also look at this transformation and see it as actually transforming signals instead of just the coordinates of the domain. Just to illustrate this effect, if I have a rigid transformation of the domain, this automatically defines a certain transformations that I can apply to the images. And if you think more in terms of the diffeomorphisms, these are the kind of transformations on the signals that live on the grid that you can get with diffeomorphisms. So this is a nice video that is by Scott Aronson, which is actually really recommended to, if I get you the slides afterwards, you can watch it completely because it goes through 500 years of different art. So I think we're going to stop at the Renaissance because we have many things to talk about. Okay, so so here again in the setting that we had is that in the language of statistical learning, we had our target function f star that was unknown, and we tried to learn this function within a hypothesis class capital F that we could parameterize as we want, right? For example, with neural networks. So the promise now that we are making is that I promise you that the target f star is G invariant. In other words, that this function f star has the extra property that if I consider any element of the transformation group and any input, I can actually, the function doesn't change, right? So that's the promise. So natural question is, how can we now leverage this promise in our hypothesis class? Can we adapt the hypothesis class to leverage this thing? And is it sufficient to break the curse of dimensionality? So we can first try to understand this question by abstracting a little bit, so not caring so much about the algorithm. So, and for this, we can introduce a very natural object that we call this group smoothing operator. So what is a group smoothing operator? It's an operator that takes any hypothesis, F, and replaces this hypothesis by the average over the group. Okay, so we replace the hypothesis F by basically an average over all possible transformations, compositions of this hypothesis with transformation on the group. So more pictorially, you can think about this smoothing operator as basically averaging all the predictions. So if we're going to predict some property of an image, we are going to average the prediction over the orbits of the group. And I believe that Taco already introduced you this language of orbit, right? So an orbit of a group centered at a certain element X consists of all the possible transformations of this image, of this input, by the elements of the transformation group. Okay? And so natural question is that now, if I have this promise that F star is invariant to the group, what can we say about the relationship between the smoothing of F star? Someone wants to try to guess? If I take F star and I apply the smoothing, what do I get? Any guesses? Okay, I don't see the chat, but let me infer that someone guessed it correctly. So yeah, the natural observation is that, of course, if the function is invariant, then it's not affected by the smoothing at all, right? Just almost by definition. So this, of course, also suggests that you give me any hypothesis class capital F, and let's try to make it G invariant by simply applying the smoothing operator, right? So because if the target is smooth, it's invariant, why don't we just restrict ourselves to hypotheses that themselves are the smoothing of some underlying original hypothesis? And just as an example, just to see how this mechanism works, think about the grid that contains just the D elements, right? So D nodes on the grid, and we just create this periodic boundary just to make our life easier. So here we can consider as a first example of an invariance group, the group of all cyclic translations, like shifts. And let's consider as our hypothesis class the space of polynomials, let's say, of degree k, right? So all the polynomials of degree k that I can express in the variables x1 to xt. So that's a question for you, and this is a code that I will use this lecture, and I'm hoping from now on, when you see like something in bold purple, it's like an exercise for you. So an exercise for you, a question for you, is to try to, in these very simple assumptions, try to write down what is the invariant class that results from these two objects. Okay, so you can think a little about it, and you don't need to answer it in real time, but that's a reasonable, simple exercise. And of course, now we can change the question by changing the group, right? So now, for example, let's say that now our invariance is stronger than just cyclic shift, but just any permutation, right? So that corresponds to this like complete graph that I think Michael already showed you in the first lecture. So we can now ask the question: if I change this invariance class, so if I change the invariance group, how is this resulting set of hypotheses going to be changed, right? And the intuition, of course, is that the larger the group, the smaller the invariance class. Okay, so and I think also this is something that Taco mentioned to you an hour ago. That seems also quite intuitive, but it's also sometimes good to make it a bit more formal, is that the approximation error is not affected by G-smoothing, right? So more precisely, if I look at the best approximation, at least if I think in terms of a L2 error, like a regression, so the best approximation I can make to F star with my hypothesis class is equal to the best approximation I can make by restricting my hypothesis to be invariant. And why is that? So if you wanted to show that, the proof is just, it's like this one of these results that the proof is one line. Okay, so the main observation here is that the smoothing of a function is an orthogonal projection, right? If I take if I look at this operator that is acting on hypothesis, this is an orthogonal projection. So in other words, I take any error I make in the prediction, I can decompose it into the error I make on the image of this operator plus the error I make on the orthogonal complement. And because my function f star only lives in this image, then any prediction that I make here, the error that I make, I can always think it in terms of the error I make in the invariant part plus the error that I make in the orthogonal complement. Okay, so obviously the best thing I can do is to just forget about this term here and concentrate all my efforts in the image of f star. And I guess you guessed at this point that this person here is the Pythagoras, right? This is just an instance of the Pythagoras theorem. So this basically also mentioned that the statistical error is going to be reduced, obviously, because I make my hypothesis class smaller, and the approximation error, as you have just seen here, is completely not affected. But of course, the question is how much, right? I mean, is this just a qualitative statement, or can we quantify the gains? So this is actually an interesting question that just how happens that has been addressed pretty recently by some works by some of our colleagues in Stanford and Song Mei, who is at Berkeley, and also people from my group. Alberto Bietti is the main author. He's a postdoc in my group. And so let me try to give you the main ingredient, the main gist of these results. So we can start by asking this question by looking at one of the classes that we studied the first week, which is the Lipschitz class, right? So let's take the space of Lipschitz functions, and let's consider their smooth version by arbitrary group G. So remember that the Lipschitz function is such that the difference between f of x and f of x prime is controlled by the Euclidean distance between x and x prime. So now if I consider this the smooth version of this class, now you can see that the corresponding notion is that instead of being Lipschitz with respect to the Euclidean distance, now these functions are Lipschitz with respect to a distance that takes into account the group structure, right? So more pictorially, here is, I don't know if you see here on the corner, is that the function, right, is Lipschitz with respect to the distance between orbits, right? That's measured between this green distance, right? So this given a point x, the distance from x to x prime is just I'm free to actually look at any point in the orbit and look at the smallest distance. Okay, so this is in fact, of course, it makes the Lipschitz assumption much stronger, right? Because the distance is much weaker, and so you can the main result that we have in this work is that in the context when one tries to use just basically kernels to learn Lipschitz functions, by using the knowledge about the group invariant into the kernel, we can actually make the generalization error of this function. We can actually have quantitative gains in sample complexity by the order of the size of the group. Okay, so here let me just unpack this notation for you, and this is also something that we discussed in the lecture number 2, is that the generalization error, right, is going to be upper bounded by the number of samples, but now instead of having actually the number of samples to the -1/d, as in the standard case of Lipschitz functions, now it's the number of samples times the size of the group. So there's a couple of lessons here. Is that the first one is that this prefactor here can be very large, can actually be exponential in dimension. And I'm not going to go here too much into the details, but if you think, for example, that G contains local translations can be the number of possible local translations is actually exponential on the size of the domain. Or even if you think, for example, about permutations, right? If you think about like symmetric functions. So this object here can be very large. But however, there's pretty bad news here is that the rate is not changed, right? The rate is still cursed by dimension in the sense that if you want to make the generalization error twice as small, you still need to increase the number of data points by something that is exponential in dimension. So this actually gives us this result, as I said, is stated as an upper bound right now. But there's tools actually using classical results from Olivier Bousquet and Ulrich von Luxburg that use a certain duality theory for Lipschitz functions that makes us relatively confident that this thing could be actually tight. So if that's the case, what this actually says is that the asking for invariance, like introducing these symmetries, global symmetries, might not be sufficient to break the curse of dimensionality, right? In the sense that there's no, we still cannot change this rate. Any questions from this slide and from the slide so far? Because I'm not seeing any chat or anything. So okay, well, please let me know if there's any questions. So far, what we have seen is that the global symmetries, they're known. Of course, using these global symmetries should be a no-brainer, right? Because why wouldn't you use them? They are going to give you better statistical error without any loss in approximation. However, there's two main things so far that we should be aware about. The first one is that it's likely that it's not sufficient to break the curse of dimensionality, right? There's something missing in this picture. And the second one is that what I told you so far is more like a theoretical question, right? I mean, I didn't tell you how to build such invariance classes, right? This smoothing operator that I described is not something that you would like to implement directly in a computer, right? Just because these orbits, averaging over the orbit of the group, might be quite impractical. So how can we do that efficiently using first principles? Okay, so let's move on. Unless I have questions, I'm just going to be slowly moving on. So now let's try to see how to go beyond group invariance, and let's try to talk a little bit about scale separation. So you might actually have seen through listening to talks from different people, even like important people like Yoshio Benjo or Jan LeCun, that it's often colloquially said that the reason why deep learning works is some sort of compositionality, right? And Yoshio uses some language to express it. Jan uses another different language to express it. There's also evidence from the brain that the brain is also organized somehow hierarchically. And of course, this idea is not just an idea that was developed by machine learning, deep learning researchers. It's an idea that has been around for a long time in the computer vision community. For example, the people have tried to understand process object like images as a hierarchy of different parts, right? That can be even deformed. The question here for us is more like, how can we formalize this intuition, right? Because it seems like we all share this intuition that compositionality should have some role in understanding the effectiveness of deep learning. So one possible way to formalize this intuition is, again, to look at physics and to look at different areas of computational science. And we see that throughout all these different areas, there's the notion of a multiscale structure is an idea that is really, really, really important at the core of many disciplines, right? Like here, I am just showing very simple examples of this idea at play, right? So you have examples in computational biology, where coarse grain, if one wants to understand how biology works, I guess that it's important to understand the process at different scales, right? There's things that you can understand at the level of doing molecular dynamics. There are things that you can do more at the level of functional maps, etc., etc., etc. Here I'm also showing you pictures of like a turbulence. Turbulence is like one of the, I would say, the most beautiful models in mathematical physics, that it really exhibits this very interesting communication across different scales, right? If one wants to understand like the mathematics of this kind of, how, let's say, how weather works, or, any fluid works in a certain domain. I mean, this is like governed by what's called a Navier-Stokes equation, which is very notoriously hard to understand, right? But clearly, the researchers have really understood that you once need to understand these at different scales. Here's a model of percolation. That is another very beautiful model from mathematical statistics, where if you once want to understand, like basic properties of this process, one needs to think in terms of different scales, right? I mean, what happens here at the level of the little corner here might give you completely different information than if you look at this from a bit more like a global perspective. And here I can go on and on and on, right? I mean, you could probably have your own examples of systems that have different behavior at different scales. So in the context of, in our context, right, if you want to relate this notion of multiscale in the context of processing information from geometric domains, we can really think about, we should really zoom in into the notion of multi-resolution analysis. And just for simplicity, in the next slides, I'm gonna focus I'm gonna focus on the grid. But keep in mind that many of the things that I'm gonna talk about can be described more generally, right? One can think about multi-resolution analysis on all the domains that you are gonna see in this class. So let's think about the 2D grid, omega, kind of a grid of pixels. And so a multi-resolution analysis, and again, being quite informal here, in the interest of time, is really like a scheme to try to decompose a signal that lives in that domain in terms of a signal that lives in a smaller domain, in a coarser domain, right? So here, if you look here at the top right, I look at my grid of pixels, and now I consider it like a coarser grid of pixels, right? I want to have less pixels. And the multi-resolution analysis, what tries to do is to try to understand how to go from one resolution to the next in a way that I'm certified to be able to keep information, right? So the way it's done is that I think about my image, my image here as a decomposition of the same image but lives at different resolution, plus the details that I need to go back, right? So it's a way to organize information. And it's important to understand that by doing this, by changing the resolution of the grid, we are really attacking the rate in this course of dimensionality, right? B, right, in the rate I gave you before, was really the number of pixels. So if one really wants to change the rate, it's natural, very natural, to try to change the size of the grid, right? And that's really at the level of a very simple intuitive idea. And so we are going to see more about how to implement this kind of multi-resolution analysis in lecture 7, where we are going to do like a zoom in on the grids. But for now, what the property that I want you to keep in mind is that the way to actually do this coarsening is through filters that are localized in space, right? So wavelets, we are going to see them in more detail, are a particular collection of filters that that manage to get this multi-resolution analysis through filters that are localized in space. And this is actually a tool that goes far beyond machine learning, far beyond deep learning. It's a fundamental tool that has really transformed signal processing. And we are going to see also in these lectures how this provides a perspective that is actually a different perspective that you get from Fourier analysis. Fourier analysis is a very beautiful, powerful toolkit that we can use to understand very well global properties, in particular its global symmetries that Taco has been introduced. Many of the interesting properties of these global symmetry groups can be obtained, can be understood through Fourier analysis. Some of the things cannot be done with Fourier analysis, and this is one of the examples, right? Like multiscale methods, they have a nice complement with respect to Fourier. So what is the link between this way to view, to understand, to process images or like high-dimensional signals and our problem in learning in high dimensions? How can we combine this idea of multiscale with priors in learning? So here's let me just give you a first example of how this thing would be combined. Suppose first that the unknown function f star, I tell you that it's a function that you can approximate, right? Instead of thinking that the input of the function is like the input image, it's a function that you can also define on a coarsened version of the image, right? So just to think about the problem that the function that you need to figure out is whether there's a beach or a mountain in an image. So do you think that for this function, you need to know x at the native resolution, or do you think that you can afford to just see things a little bit more in a coarser scale? For example, I blurred here these things a little bit, right? So I guess that all of us would still be able to say whether we are in a beach or we are in a mountain. And by the way, this is one of the very beautiful beaches. I don't know if you would think that this may be some Caribbean place, but it's actually in Spain. It's in the north of Spain. It's in Galicia. And this is also in the Pyrenees. It's not far from my home country. So here is an example where the coarse scales dominate, right? So here, if I want to approximate this function f star, I can perfectly focus on the core scales. And obviously, because the dimensionality of x tilde is smaller, right? I mean, if I can do everything by throwing x and just keeping x tilde, I'm winning, right? Because the size of the grid is smaller, so coarsening reduces the cost of dimensionality. So this seems like an easy shortcut to our headache. Of course, this is not true in general, right? I mean, this is an example. This is a kind of a simple problem to solve, right? Detecting whether we are in a beach or a mountain. There's many problems in recognition that are going to become hard, even impossible, if I smooth too much. For example, here, it's not clear that we can still recognize what are the digits by just looking at the core scales. So fine scales are important in general. There's another alternative situation where the multiscale structure can also help us. There is in a sense, in some sense, it's like the dual situation. So here, assume that the f star is such that the f star of x can be well approximated by a sum of local terms. And what do I mean by local terms? Think that here x of u corresponds to extracting a patch centered at pixel u, right? So this would correspond to one particular patch. This would be another patch, etc. So for example, like texture, recognizing if you are in a brick wall or in a bunch of grass is one of the examples that falls into that category, because here is really like the local scales dominate, right? Like here, what matters, if I want to get like a good classification here, obviously what I need to do is to average local descriptors that I see, just because there's not a lot of variability at core scales, right? I mean, the texture by definition is a structure that has some kind of like spatial homogeneity. And this idea is, of course, and here, of course, we can also see that the curse of dimensionality is avoided, just because the relevant dimension in this problem is really the relevant size of the input is no longer the size of the input image, is the size of the patch. And if you want to get more details, on how this thing is actually quantified, there's a nice, beautiful paper from the group of Matthew Wyatt at the EPFL that gives you the details. The references I'm gonna give them to you offline. There's another instance where we have this notion that the function that we're interested can be thought as basically something that is linear with respect to local potentials. And this is really at the core of modeling with local Markov random fields. Probably if you have followed the class on probabilistic graphical models, you have seen that these are also like a pretty popular model to model for high dimensional data that just tries to model the joint density as a combination of local clicks. And for example, if you want to understand this in the context of particle systems, if I have a particle system whose Hamiltonian, right, the energy of the system can be seen as a sum of local potentials, this is an example that falls into this category, right? Like the thing that drives the complexity, the sample complexity is no longer thing that is exponential in n, but things that are exponential in p, which are here the number of different particles that I need to see at the same time. And if you are familiar, if you want to figure out an example of this such a system, if I think for example like an n-body system, right, the gravitation, like mechanics, right, Newton mechanics, the dynamics of n planets, the energy is just a combination of pairwise interactions, right? So I don't need to understand to process like arbitrary clicks of planets. I just need to understand pairwise interactions. But of course, as I said before, this is in general not sufficient, right? Because we can, of course, think about many situations where just by looking at local statistics, we are not going to solve the problem, right? Here's a beautiful, cute example that I took from Turk, like a SIGGRAPH paper from many years ago, where of course, if you just look at the texture and combine the texture with an arbitrary shape, texture alone is not sufficient to understand the content of the image. So somehow what we need is to think in terms of like try to combine these two extremes that we described before, right? Like we want to really illustrate, capture the fact that we might have information in the core scales, we might have information in the fine scales, but somehow they interact in a way that is not too strong. And so here we can consider a general compositional model that takes this form, right? So we take as like the input again is a signal that maps a certain input grid with a certain number of channels. Think about this like input C to be like, let's say the RGB channels. And so here what we think is that we can try to view, like to approximate our function f star as a composition of two operators. One that is just applying some kind of like a nonlinear local coarsening, something that is akin to extracting the coarse scales, but maybe with a bit more, structure, a bit more capacity to approximate more complicated things than just like a linear coarsening, combined with another function, right? With a function f tilde that is going to extract some information at the coarse scales. In general, it has to be more powerful than just simply looking at the average, right? That's the example we saw in this like weak scaled interactions. So a priori, we need to actually put parameters both in P and F tilde. Okay, so natural question, of course, is that we introduced this compositional model. When can we actually argue that this compositional model is more efficient? So here, somehow we can really argue in terms of like a particular examples, right? Here I have to say that there's like the general structure that really tries to classify, to organize exactly when precisely these compositional models are going to be better. It's still like something quite nebulous, quite not completely understood from a theoretical perspective. But we have, of course, instances where this thing is obviously a winner. You might, of course, in context of dynamic programming or like algorithms, you are probably familiar with these methods of divide and conquer, right? That there's a class of problems, algorithmic tasks, where it's obviously a benefit to try to think about the problem in terms of like breaking it into smaller problems. There's examples in approximation, like Matus Telgarsky has this very nice work where he shows that composing different value functions is much more efficient to approximate functions that have this very simple periodic structure, right? If you have a periodic structure, you might be better off trying to approximate it with a composition of values than directly. And there's also very pioneering work by Tommy Poggio and some of his collaborators on really quantifying the benefit of functions that can be expressed as basically hierarchical compositions of simple coordinates. So even though we don't have like a perfectly clean theoretical picture yet, one thing is obvious is that we can right away already combine these two priors of the scale separation and group invariance to give a very simple, like powerful model from first principles. And that's the third part of my talk. And let me just maybe pause for a second and ask for questions, because as I said, I don't see the chat. Okay, so I see that there's a lot of questions here.
There are two questions. Yeah.
Yeah. So I see the question that, wait, let me just try to go by order. How big? Okay, so the same function, blah, 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 blah. So let me first try to address a very concrete question I see from Jama, who says that coarsening reduces the course of dimensionality. How coarsening reduces the course of dimensionality? Right. So this is really the intuition here is that the course of dimensionality, what does it mean? It means that the number of samples that you need is going to be exponential in the dimension. What is a dimension in an image? It's proportional to the number of pixels. So if you coarsen the domain, you reduce the number of pixels. Therefore, you improve the exponent in the sample complexity. Obviously, one cannot just brutally take your input and coarsen it, right? Because if you just, what I try to justify in this part of the talk of the lecture, is that one should be careful, right? Just brutally throwing away high frequency information might destroy the content, right? Might make the prediction very complicated. So the way in which the coarsening needs to operate is something that has to involve also some nonlinear processing. So, but the key idea that by reducing the size of the domain, we are breaking the course of dimensionality. That's something that I'm hoping that it's clear. So let me just now look at another question. Can we also link fractal notion to the course of dimensionality? Good. I mean, this is actually a very interesting question. So I don't know if the person like Benjamin that you were thinking about fractal in the sense of self-similarity, right? If I have structure that has some statistics, like the fractal structures, they are characterized by something that is similar at different scales. For example, if you zoom in the fractal, you get the same thing all the time. So that's an example. That would be an example of a very, very, very strong prior, right? Because if you promise me that what I need to process is a fractal, then a priori I could just extract information at one particular scale and I would be done, right? In a sense, I might have the impression that my input is very, very high dimensional, when in fact, I just have the same information that is repeated again and again and again at different scales. So that would be like a simple way to leverage this property. So in that sense, like the self-similarity is something that could be used to actually help us in breaking the causal dimensionality. Of course, there's a lot of fractal structures that are not as simple as that. For example, some of the turbulent examples that I showed have a little bit of self-similarity, right? They are what's called multifractal, but still we cannot just simply we don't have the luxury to throw away scales. So I think that I mean, definitely it's very interesting and very related, and there's still a lot of interesting things to do in that front. Okay, so if there's no more questions, I'm gonna move on. So how can we combine invariance?
Sorry, Joan.
Yes.
Yeah, there's one more question on campus wire. Maybe I could read it to you.
Sure.
Yeah, so it says, how can scale separation deal with the noise in the data? I mean, what if we added the noise at different scales of our image, for example? How can we leverage scale separation and G invariance to deal with this?
Yeah, so that's a good question. So and this is really where an instance where using tools from signal processing harmonic analysis is helpful. Why? Because this multi-resolution analysis that I described, they are really designed to be stable with respect to noise, in the sense that there's a promise that if I look at the input and I process it I decompose it into a signal at different scales, the noise is not going to be amplified, just because I have designed the multiscale approximation to be like that, right? So I define it as what's called a frame, like a linear frame that is stable to noise. So in that sense, the design, like this is really the role of the engineer or like the machine learner to really set up, like design a multi-resolution analysis that is stable with respect to noise. Obviously, there's there's things that sometimes can go wrong. For example, something that I didn't talk about here, but if one, for example, naively tries to incorporate different levels of compositionality in your architecture, you might make some of the problems harder. And this was actually what happened in the early days of deep learning. If you try to train a network of, I don't know, like 20 layers, well, it didn't work because the way the compositionality was normalized was maybe was parametrized, wasn't stable. Gradients would explode or gradients would go to zero. And so this is an example where it's not always a winner, right? Like this compositional structure needs to be parametrized and designed with care in order to make it work. And so I hope that this partly address the question. Of course, I'm happy to go afterwards in Campus Wire to follow up. Okay, so let me move on. So here we are going to now talk about how to combine invariance with scale separation. So as I said, like just remind you the wish list. We want to combine. We're going to have a function class that is invariant to the group action, and it incorporates this multi-scale structure. And also that is a rich class, right? So I can potentially, I would like potentially be able to approximate arbitrarily well any target function that is both invariant and multiscale. So how can we connect these kind of wish lists, like these axiomatic principles, with an architecture? So an interesting way to proceed is to really start by trying to characterize, to classify the operators that have nice interaction with the group. So we can start with linear operators, right? So we can start from a linear operator that is invariant to the action of a group. So I might ask a naive question. I give you a group and I give you some space in which this group is acting. How many linear operators are invariant to the group? So in fact, you might, there are not so many, because by very simple algebra, right? So here I have again, it's like one of the things that I like. It's like a one-line argument, is that if I have a function f that is both linear and G invariant, first, by the first equality here is using the G invariance. So f of x is equal to the average of f over the orbit, just because it's invariant. And because the function is linear, I have the second equality, right? Because the function is linear, I can put f outside. So what I see is that any f that is linear and G invariant is actually a function of the average of the input over the orbit, right? So I can always think about such an operator as taking as input not x, but the average of x over the orbit. Okay, and if you think about, just to get the intuition, think about the group being the translation group, and x being the space of images. So the orbit of the translation group over an image would consist in all the possible averages of the image, right? So the only thing that remains is just the image average, right? Like the RGB values. And so the group average here is an important object that basically is the only linear operator that is invariant. So this, of course, is an operator that loses a lot of information, right? I mean, if you only look at the average over the group, it's like, think about an image, right? You have 1,000,000 pixels. If you do the group average, you only have like 3 numbers, right? Like the average R, the average G, and the average B. So we certainly need more to be able to do classification than just the group average. So how can we complement this? And again, so this is something that also Taco introduced. We can complement invariant with equivariance, right? So equivariant are operators that instead of being invariant, they commute, right? So this is the equation that I think Taco already introduced to you, right? So if I have 2 spaces, right, x and y, and a mapping that goes from x to y, I say that this mapping is equivariant if in a sense, if it commutes with the group action. And this equivariance is going to be with us through many lectures, right? We are going to see equivariant in many, many contexts, in the context of grids, in the context of groups, in the context of graphs, etc. So how can we actually combine equivariant with invariant? So how can we actually extract more invariance from the equivariant features? So first, maybe a first intuition that you might have is that, okay, why don't I just first consider an equivariant, linear equivariant, and then I compose it with a linear invariant? Does it work? Well, actually, I just put it here as a purple exercise, right? So if I compose a linear equivariant with a linear invariant, it doesn't work. And it's a good exercise for you to try to figure out why. So what is the alternative? So if just directly composing linear equivariants doesn't work, then I need to do something else. So obviously the alternative is to consider a nonlinear operator, right? So like a nonlinear operator that acts element-wise, right? So what is a nonlinear operator that acts element-wise? Is a mapping that, let's say, maps images to images, but this mapping can be understood, right? The mapping from the left picture to the right picture is the same mapping that I apply at every pixel, right? So it's like take as input as a whole image, but in fact, every pixel is treated independently, right, from a arbitrary nonlinear function. So it's immediate to see that if I have a linear equivariant B and I compose it with the element-wise function rho, I automatically gain a nonlinear equivariant, right? That's also like a simple exercise that you could try to work out by yourself. And moreover, if I make it such that these equivariants are local, right? So they are local in the sense, as I said before, as local in the sense of a multi-resolution analysis, then because I'm composing with an object that has no receptive field, right? But like this operator here is actually element-wise, the receptive field is not increased, right? So B tilde is also local. So this actually gives us all the ingredients we need to define this geometric deep learning blueprint, right? So we can have a very simple constructive approach that we can use to define very general architecture that is compatible with our assumptions. So what are the ingredients? What are the building blocks of this blueprint? So these are all of them. We have described it. So just to repeat, we have a equivariant layer that is linear, right? So this is something that we can hope to understand very well, because understanding linear maps is always easier than trying to understand generic nonlinear maps, right? So like we start from just linear, understanding very well the linear equivariant structure. We can then compose these linear equivariant maps with the element-wise nonlinearity. We can combine these equivariants with like a coarse graining, right? Like in a multi-resolution analysis. And at the end, we can, once we are at any point in the process, we can extract invariance by applying our group smoothing, our group average. And so one of the power of this blueprint is its generality, right? That it's the same blueprint that one can apply throughout the different domains, right? The grids, the groups, the graphs, the manifolds, all of this. And this is probably the picture that you have seen that hopefully captures a little bit this intuition, right? That we can really visualize what these networks are doing as a composition of very simple tools. And let me also say that this construction is, again, by no means we are the first ones to propose this architecture, right? Works, for example, by Trivedi and Rishi Kondar already studied and provided very interesting analysis of this kind of construction. And this is something that more like a hint of what's going to come next. This blueprint can be instantiated in many different domains, yielding very well-known architectures, right? Like the architecture that you see here can be really understood through the lens of our blueprint by just plugging the domain and the symmetry group. Okay, so just as a takeaway, as a conclusion, to try to wrap up what I tried to talk to you about today, is that we have really seen through both my lecture and Taco's lecture today that geometric priors that can be articulated in terms of symmetries and scales really give us like a new vocabulary, right? To define new hypothesis spaces that together have some ability to break the curse of dimensionality. What I try to tell you today, to warn you, is that one should really think about these things in combination, right? Symmetries alone might not be sufficient to break the curse of dimensionality, right? I try to give you evidence by just leveraging analysis using kernel methods. What we have is that just in terms of like postulating these hypotheses, right? We can connect them. We can make them actionable, right? So we have group invariance is something that is useful directly to define architectures, right? So through this, through the language of invariance and equivariance, we can proceed if we understand very well linear invariance and linear equivariance, then we have a very simple, flexible language to construct function classes that have all these hypotheses, all these assumptions that we like. In the theory side, there's still a number of very interesting open questions. So for those of you who are more interested in the analysis and the theory, for example, I haven't given you like very precise definition of the scale separation, right? I just tell you that there's this composition, but we haven't really precised what are the hypotheses, what are the function spaces that we assume in each of the two terms. This is still pretty much on the making. In the next lectures, we will spend a lot of time trying to instantiate this blueprint on different domains and in particular trying to go a little bit, zoom in into more of the analysis, right? So we are going to study things that become specific when one has graphs, grids, manifolds, etc. So with that, I think that was my slide. And so I think we have 5 minutes for questions. Thank you very much.
Hi. I have a question related to scale separation. You mentioned it in the last. Yeah, you didn't mention how much scale separation reduce the case of dimensionality.
Hello? Yes. Yeah, I mean, as I try to argue here, if one takes the kind of extreme cases of scale separation, like I cover the two extreme cases, right? Where one can use like a linear coarsening followed by an arbitrary mapping. On the other extreme is that one has this like a weak interaction, right? So just local structures matter. In these two cases, it's pretty clear, right? How one can break the curse of dimensionality, right? In the first case, because the size of the grid is reduced exponentially with the number of scales. And in the second one, because the relevant scale, like the relevant dimensionality is the dimensionality of the patch. What happens in the middle, as I said before, is still pretty much in the making, right? So one should expect that the actual benefits are somewhat interpolating between these two extremes. But as I said, just as I mentioned, just to make it sure, I mean what is clear is that this prior is critical, right? If there's no scale separation, then as I said, as I told you before, even though you might have this like invariance, like global symmetries, these symmetries alone are not going to break the curse of dimensionality. I hope that this answered your question.
Yeah. I thought like there is no general theorem like the one in symmetry. You reduce approximation error by.
Yeah, I mean, this is really this example. This is also an instance of kind of a total. It's very easy to build tautologies here, right? Because I can say, okay, if my target, I can build a target class that is parameterized by a certain hierarchical or multiscale architecture. So if I promise you that the target is in that class, obviously I'm not going to have a curse of dimensionality because I parameterize this class with a number of parameters that is not exponential. So I guess that the more interesting question here is to really try to characterize like intrinsic properties of the target function that enable or that make this multiscale architecture sufficient.
Hi, Joan. I have a question.
Yes.
The order of the blueprint matters, right?
Yes.
Particular
yes. Yes. The order matters. Yes. Yeah, actually, that you're totally right. The order of the architecture of the blueprint matters in the sense that if, for example, if you first started from an invariant model, right? The first thing that you do is just look at the average. Then you will throw away all the information, right? And so the order in practice, of course, matters. But yeah, I mean, and again, the way I define it here is pretty high level, right? So we have roughly 3 different things that you can do. You can either take invariant, like group averages. You can propagate information using equivariant followed by a element-wise nonlinearity, or you can do like a coarsening. And so the choices, like the ordering of these blocks, is pretty much determined, right? I mean, there's an order that is kind of canonical, and that's the one that if you look at the different architectures, neural network architectures, that's the one that they implement.
Okay, so do you also have an idea about the depth, for instance, how many equivalent layers we could stack in order to fully capture the features?
Yeah, that's a good question. So here I didn't, it's true that I didn't mention it. I didn't put an emphasis here, but what this multiscale architecture suggests is that the depth of the network somehow grows or like is related to the number of scales, right, of the image. We know that this is not necessarily, it's not precise, right? Because if you, for example, the ResNet architectures in the modern days, they have many layers, and in a sense, like they are a little bit detached from the number of scales. So I don't want to make any kind of like a strong claims, but the intuition is that somehow the role of the depth is to precisely process the information, to propagate the information towards the coarse scales. At least one of the roles of depth. We don't know exactly. I mean, the role of depth is a notoriously hard question to understand. And so we to be honest, from the mathematical, like if one wants to really have like a rigorous mathematical answer, it's still escaping us in a sense. But that's something I'm very interested on. So if anyone here is interested, I'm very happy to chat with them.
Okay, hello, Mike. So please, are we able to quantify the exact contribution of, I mean, this scale, I mean, separation when it comes to the representation of high, I mean, dimensional data?
Yeah.
And so what is the exact contribution that it actually adds? I mean, in combination with other sort of transformations that do okay.
Yeah, so the exact contribution of the scale separation is really to avoid having to process all the pixels together, right? So this idea that I mean, the course of dimensionality is really coming from the fact that if I need to capture like arbitrary patterns that might be present in the collection of like 1 million pixels, I basically need to look at all the possible subsets of million pixels, right? If I have no assumption of where the patterns will be. So the scale separation is basically telling you that you can first focus on extracting local patterns, and these local patterns can be recombined together to form like larger patterns, but somehow you can afford to just assimilate, to associate a group of local pixels together. So as I said before, how exactly, is there a theorem that tells us precisely the gains of scale separation for a particular hypothesis on the target function? Not yet, but I think that this theorem is there, right? It's just waiting for us or for you to be formalized. But I think, as I said, I mean, if you look at the different extremes, right, like the different extremes of this scale separation, these we have already some papers, right, some theory that really quantifies the benefit of scale separation.
Okay, so thank you. So like as a follow-up to, I mean, Faisal's question, for which he asked, I mean, about how scale separation deals with the noise in the data. Yeah. So one thing is, I know one easy way of removing noise from data is just by averaging the image. Yeah. So so like comparing the work of, I mean, scale separation and that of, I mean, just normal averaging of the pixel, maybe the weighted average of the pixels from different images to actually denoise an image. I mean, how do they differ in terms of, I mean, their performance?
Yeah, I'm not sure I understand the question. So you're asking that how do you use the multiscale representation to remove the noise?
No, if okay, that's not what I'm actually talking about. So, like, you know, when you talk about using the scale separation on, I mean, on data that is very noisy. Yeah. So, and I also know that, I mean, if we want to remove the noise from just, let's say, a normal data, all that you can do is you can average the pixel, and then you just use the average, I mean, to represent all the pixels in the image. So I am asking that, in that context, how does the averaging of the pixels differ from the use of the, I mean, scale separation?
So yeah, in fact, they are very connected, right? Because if I think about like, if you want to just look at the local average, you are essentially doing the thing that I shown in the slides. You are basically throwing away the details, right? You are just removing you are just pushing the image and keeping the low frequencies. In fact, there's things that you can do that are like strictly better than that, right? Even for the context of just removing the noise from the image, that in fact, are closely connected with the properties of this wavelet decomposition, right? So if you are familiar a little bit with image processing, this multiscale representation, right? If I just treat it not with the goal of learning, like a classification problem, but just to better represent the image, we have a very important property here that is the sparsity, right? It's a property that we haven't really discussed about in this lecture, but it's in a sense like pretty deep into the properties of these models. That is the fact that you have a decomposition that is sparser. And so when it's sparser, this enables a class of methods to remove the noise that are based on what's called a thresholding, right? If you just keep the coefficients that are bigger than a certain threshold, and then you reconstruct, you are able actually to remove, to improve the signal to noise ratio. And this is really like one of the, let's say, main products of multi-resolution analysis, like one of the reasons why it's still so popular today is because they are very powerful methods to solve inverse problems, in particular to remove the noise. So connecting to what you were saying, if I have a lot of noise in the input, I can still, I mean, it makes even more sense to think about like a multiscale representation, because in a multiscale representation, I can really, it's easier for me to remove the noise, right? Because I can just concentrate on the coefficients that are bigger than a certain threshold. That's not something that you can do if you look at the pixel domain, right? Because in the pixel domain, if you add noise, all the noise is kind of affecting all the pixels the same way. That's not the case if you are in the wavelet domain. I hope that this answered your question a little bit.
Yes, for sure. Thank you.
Yeah.
So are there any more questions? Otherwise, you take the rest on campus wire.
Yeah. Okay. Great. Thank you very much. And I think that today there's the seminar right now.
Yes. That is in 2 hours.
In 2 hours. Okay. Okay. Perfect. So
Yeah.
okay. So thank you very much, and I'll be looking at campus wire.
Yeah. Sure. Thank you.
Okay. Bye-bye.
Bye.